Hey everyone, it's Scott here, and today I would like to go over Karnaugh Maps. So you're probably wondering, what are Karnaugh Maps? Well, Karnaugh Maps are a way of sort of basically mapping input to a given output. And if you're given a certain output from a truth table that is dependent on certain combinations of ones and zeros by a certain amount of variables, it can be like 2 variables, it can be 3 variables, it can be 4, it can be a bunch of variables. But regularly, when we have a Karnaugh map, we're only dealing with a maximum of 4. But the point is, what we want to do is we want to take our output from our function and make a circuit as simple as possible. Now, a Karnaugh map enables us to do that. So, as you see here, we have this output here. And what we're going to do is, depending on these combination of inputs, we're going to map it to these cells, which will then give us an equation. So what we need to know for today to map our truth table to the Karnaugh map is following these rules here. Now, I'm going to only focus on min terms for this video, and I'm not going to cover don't care. So I'm going to try to keep this as simple as possible. But what we are going to cover is how to make a Karnaugh map, how to then make an expression from that Karnaugh map, the simplified expression, and then implement that into a circuit. So here are the rules. A group can only be anything 2 to the power of n, where n can be any arbitrary number that is whole. This grouping, however, cannot be bigger than the k-map. So this is an important rule. You can't have groups of odd numbers, and you can't have groups of certain even numbers like 6. You can only have groups 2 to the power of n. So if it's not a group that is possible, a grouping of bits in the Karnaugh map that doesn't correspond to 2 to the power of n, then it's going to be a problem. So if you do 2 to the power of 0, it's going to be 1. If you do 2 to the power of 1, it's going to be 2. So that's the amount of bits you can have in that group. So what I'm going to do here is I'm going to look at this map here and I say, okay, I have this output given these corresponding possible values. So I'm going to number my cells here. We count cells starting from 0. This is 0, 1, 2, 3. And since we only care about min terms, which are 1s, we're going to map these to the cells here. So at 0, we have a 1. And at 2, we have a 1. So we know that 2 to the power of 1 is 2. So a grouping of 2 is possible. But before we get into that, I just want to highlight that there are domains that we're covering in this Karnaugh map. So for A, the domain is going to be here because there's a 1 for A. And then for B, a domain is going to be here because there's a 1 here that corresponds to that. So basically, since that grouping is possible, what I'm going to do is I'm going to grab my shape tool here, and I'm going to make a group here. Now, notice that this group, you have 1 bit that is inside A, 1 bit that is outside of A. So what that means essentially is that A is not a possible variable. It can only be within the domain of A or outside the domain of A. So since that's the case, we notice that this grouping is outside of B perfectly. No values are inside of B. So therefore, it gives us the equation. I put a little equal sign here. Oh, I got to turn off my circle tool. This will give us B negated, and the bar indicates a little negation sign there. So cool. That's a pretty simple example. I have some more. Yeah, here's like a little example here of just how Karnaugh map works. Just one thing to keep in note. Things that are on the edges can be grouped, so it can wrap around like from this side all the way around to this side, or it could go down and all the way up, although not in this example here because it's only 2 cells high, so you can't do it there. But we'll see more examples of this later on. Here we're given another map. Again, we look at the cell numbers 0, 1, 2, 3, and we say, okay, 0, 0, 1 is 1, 2 is a 1 here. Now notice that according to the rules, we can't do something like this. This is not possible. This is wrong. We can only group them vertically or horizontally. And since 2 to the power of 0 is 1, we know that 1 is a possible group. So this can be a group, this can be a group, and these are their own separate groups. So all I have to do is this. I put a little B here to designate the B domain, a domain here A. Okay, so let's start with our first group. So we know that our first group is within the domain B, however, not within the domain A, so we do A not. And then we do plus for OR operation. Remember, if there's no operation between the variables, that's an AND. We assume that's an AND. So we have an OR operation, and we move to the next grouping. A is 1, so this will be A, just regular A. It's outside of B, so it will be B negative. And you'll notice that if you do the truth table for this, you'll get just a regular XOR gate to do this, essentially. That's what this is. So B and not A, or A and not B. So moving on, we have a much more bigger Karnaugh map here. And this one's a little bit more tricky to sort of figure out. So we have our cells like before, which is 0, 1, 2, 3, 4, 5, 6, and 7. So again, looking at the map, we see that this here is a 1, so we're going to put a 1 here. 2 is a 1, so we're going to put a 1 here as well. Oh, and by the way, one important thing to notice, look at how things are numbered. So you'll notice that you have to number things in this particular way. So it goes 0, 1, and then to the other side 2, 3, bottom 4, 5, and then to the other side 6, 7. So that's going to be important to remember. This is a pattern that this is a pattern that will affect the outcome of your equation. So make sure that this is all correct. So now that we've done that, let's keep mapping. So we have 4. It's the next one here. We have 5. We have 6. And we have 7. So remember, our rule here, any arbitrary whole number n, has to be a positive number, by the way, can't be a fraction. Any whole number n groupings is possible, so 2 to the power of n. We go back here, we know that 2 to the power of 2 is 4, so this is a possible grouping here. And since we have these two ones here, right, these ones that are not covered. And just to remember, or just to recap on the rules do state that we want to minimize the amount of groups that we have. So if we have a possible group here, or a maximum amount of numbers that we can encompass that is possible, we want to do that. So overlapping is allowed. And what I mean by that is you can't do something like this. This does not work, because technically we can create an even bigger grouping that would include more ones. So this is what we want to do. We want to make this, because this is the biggest possible grouping to group all the min terms. So again, we look at this, we write out our domain, so let's do that right now. So this is A. So if we look at this carefully, you'll notice that we have more possible combinations here. We have B, C. So you'll see here that B is on the left, C is on the right. So when C is 1 on the right, that's our possible grouping. So down here, we'll mark this as domain C. Oh, that's a bad C. C, because we have these here, these ones. Remember, these are the only ones on the right-hand side where C is. And then we have the possible we have the ones here on the left. Those are the only ones that are on the left. So I'm going to put domain B here. So now we have this grouping. These groupings and these domains mapped, we can write out our equation. So let's start with this grouping that spans across. We remember that if it's partially inside of A is not an included variable. So A doesn't matter. It's partially inside B, so B doesn't matter. It's perfectly outside of C though. So what we can do is C bar, which is C negated, or, and then we look down here, this is perfectly within A, so we just put A, put the little equal sign here. A, it exists, again, outside of B, outside of C, so we don't include those variables, and this is the simplest form that you can achieve here. So now that we've done that, let's move on to another example. We have an even bigger example. Again, this shouldn't be terribly difficult to do. In fact, let's number our variables. So we have this one here, 0, 1, 2, 3, 4, 5. Ooh, that's terrible. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so we have 16 possible outputs from these given combination of variables. So again, to reiterate, we're going to look at, A and B. So A is on the left, B is on the right. So we look at the ones that are grouped on the left. So this is going to be A. And the other side, remember, we're grouping the ones here. These here are B. So we're going to name this B. This here, that's going to be C. This will be D. As a terrible bracket there, but anyways, we're going to look at this map here again. So 0 is 1. And remember, to number these properly, 0, 1, 2, 3, 4, 5, 6, 7. However, this is a little bit different, where instead of counting downwards and, to the right and then to the left, we go down to the bottom and continue counting, but then up. So 8, 9, 10, 11, 12, 13, 14, 15. So just keep that in mind. So 0 is 1, 2 is 1, 4 is 1. There we go. 4 is 1. 7 is 1. 11 is 1. Put a 1 here. 11 is 1. 12 is 1. 12 is 1. What else? 14 and 15. So these are 1s as well. And again, we look at the biggest amount of groupings that we can possibly have to minimize the amount of groups that are in the Karnaugh map. So that would be, if I get out my circle tool, we can create groups here and here. Okay, so these are all 3 groups. And then we have a sort of an odd situation here where we have these ones at the corners. They can just be grouped like such. Remember, we have to group all the ones. And then this possible group is probably just like so. So that's a lot of groups, and that's going to get us a lot of minterms, or a lot of, SOP groupings. So we're going to start with the first one here, which is, we know perfectly lies outside of A, so we do A negated. we know it lies outside, just outside of C, or in between C and not C, so it's not included. It perfectly is outside of B, so we're going to do B bar. We know it is outside of D, so it's also D bar, and we should be good for that one. Then we look at this grouping here. I'm going to do OR, and this is, yeah, in between A, so that's not going to be a thing. A is not a variable, so we're going to do B, because it lies perfectly within B, outside of D and C. So C negated, that's terrible C, let me try that again. C negated, D, D negated, OR. And we got these three groupings here, so I'm going to start with this top group here. So we have B, we have C, C and D. Again, we can't include A because A, it's inside the domain and also outside the domain at the same time. And I'm going to do OR and continue down below here. This group here going across, this is automatically, you can just look at this A, B, and C, but not D. So just A, B, C. Then we look at this one, which is A, AD, and C. So ADC. A, or ACD. I think we put it in alphabetical order. It's less confusing. But yeah, there you go. That's how you do it. So we've created the expression, and that should be the smallest possible expression. Again, you could probably simplify with gates. If you understand gate logic, you could probably simplify even further. And then here's our final example, which is, here we have our given output relative to this input here. So we're going to map that. So, and 15. So now that we've numbered those, we can map them to our Karnaugh map. Again, remember how these cells are numbered: 0, 1, 2, 3, 4, 5, 6, 7. And then we go down to the bottom and go in reverse. So we go up. So 8, 9, 10, 11, 12, 13, 14, 15. So just make sure you keep that in mind. At 0, we have 1. So 1 is here. Yep. And then at 1, we have, wait, let me see here. 2, actually. 2, we have 1. And then we move on. We have 8. So 8 is our next one. So that's going to have a 1. 8 is going to have a 1, and then we go all the way down to 12. Where's 12? 12 is here. Did I skip any numbers here? No, I don't think so. So we have 12. And then we have 14. Yeah, so let's look at this again. 0, 2, 8, 12, and 14. So we have 0, 2, 8, 12, and 14. So that should be all of the terms. Let me group these. Let me get out the grouping tool. So there's multiple possibilities here that we could have. If we look here, we can have a grouping that spans across here. So at the corners, you can, have this loop around and group. Here, these can be a group. Actually, let me just use the circle tool. And we have another group which is here, extends around to here, and that's our grouping. Okay, so just to verify, yep, that looks good. This is what we should have. And now we can make we can basically note our domain. So this is A. This outside here is B up top, all right, C, and down here is D. So I'm gonna look at the top one here. We know it's outside of A, so it has A negated, and what else? B negated. It's outside of B, B negated. And it has no C because it's partially inside and outside. It has D negated though. So D negated, or, and then we move on to our next group. So let's go to this one. Actually, you know what? Let's do the 8 and 12. So that's in A. No B, because it's partially inside of B. And then there's no C and D. So C negated, D negated. Okay, now we have our third group, which is here. So that's A, B, partially in C, outside of D, so D negated. And that is our expression there. So just to verify our work, what I like to do is I like to take this Karnaugh map and put it into this tool. I'll link this tool in the description. I think it's very useful when you're first learning Karnaugh maps and how to do them correctly. So we can look at our ones and we can populate the Karnaugh map like such. So we have 4 variable modes selected. We just click on the cells. Yep, those group like that. And yes, so as you can see here, this is how the Karnaugh map should be grouped. And I think it gave us the same equation. So A negated, B negated, D negated, A, C negated, D negated, A, B, D negated. Now, it works a little bit differently. They use apostrophes to put a negation. The bar is also correct. There are many ways to symbolize negation. So just be aware of that. And without further ado, let's check our other one. This one was really big, so I'm going to reset this. And I'm going to basically set this to match our Karnaugh map. And there we go. So we have our expression here. I think that's all correct. Yep. So we have A negated, B negated, D negated. And then we go B, C negated, D negated. And then we have B, C, D. A, C, D. And, oh, A, B, C. Did I make a mistake here? Wait, no. Sorry about that. No, I didn't make a mistake here. They just have it flipped around. So it's just ACD is here, ABC is here, so we're good. And that's all there is to basically looking at a Karnaugh map and formulating an expression. Remember, you can only have groups that are 2 to the power of n, so that's anything that is 1, 2, 4, 8, 16, 32. Think of it as binary counting. If you've done binary counting before, it's the same sort of idea as to what kind of groupings are appropriate to implement in the Karnaugh map. So we have a couple of examples that are finished here. You're probably wondering, how do we implement this? Well, this is quite simple, or should be straightforward. We look at this equation and we implement the logic that applies to it. So we can take an example like this, and we can say, well, you know, this is B, not A, or A, not B. Now, this is going to take some thinking. We could just implement it like such. We could take this equation, we could have A and B, we could, you know, give them NOT gates. We could do basically A not, and then, you know, use an AND gate and like implement it like this, and then we could take another AND gate and we could do this, and yeah, have another NOT and do this like such. We could do, yeah, take an OR gate, we can OR that, and it would give us the same output, but it's not really simplified, so you're going to have to think, you know, sort of out of the box when it comes to this. Well, you're sort of just going to have to memorize the characteristics of these given gates. So technically, this is a XOR gate. So I can do either or, I can do both of them, it'll get nothing, I can do nothing, it will get 0. And you can see that this is reflected in our truth table here. So if I scroll over, you'll see that 0, 0 should get us 0. 0, 1? 0, 1 should get us 1. 1, 0 should get us 1. So that's cool, but this is a lot. So technically, we should be trying to reduce this. We can reduce this by creating a new chip here. and we can get a NAND. We can get two inputs. We can go like this, get another two NAND gates, and we can hook it up like so, right? Get a final NAND gate here, and we can get an output. This will make our XOR gate, and then we can save that chip as XOR. So if we save that, do a new chip, it behaves same way as the truth table over here. So that's how you implement it. Now, what happens if we have some more difficult logic like this? This is, again, should be fairly straightforward if you know what these logic symbols mean. We have a negated and A. And we don't even need to hook up B because guess what? B cancels out. This output here is not dependent on B. So we can just have two inputs. They're just A and C. And basically do this. We just do an OR gate here because again we need to look at what is being inputted. So it's two things, not C and A. So we do it as such. And it should match the logic of this. So if we look at our combined inputs, we notice that the combination of A0 and C1 gives us 0. But we look at this and we go A1 and C1, it should give us 1, which is true. And that's basically the gist of this Karnaugh map, is how you put it together. Now, it's going to get a lot more complicated with this Karnaugh map here. Now, notice that we have, for ORs, we have 1, 2, 3, 4 of them, and we have 5 inputs, so 1, 2, 3, 4, 5. So I like to read it like this. We can build this from the right to the left. So we know that there's 5 inputs being given, so we'll give it a 5 OR gate. And then we'll look at each of these units. We know that each of them is 3 variables, so we need a 3-way NAND. So we're going to need 5 3-way NANDs, or ANDs, sorry, 3-way ANDs. Right? So now that we've done that, we're going to need some NOT gates. So I'm going to make, let's see here, 4 NOT gates, and these are all going to connect up here. Right? Like such. And then we're going to hook up the variables to these ANDs because we're ANDing them. So A gets ANDed here. What else? B gets ANDed here. B naught gets ANDed here. C naught, or not C naught, sorry, D naught. D naught gets ANDed here. B, we have regular B, so we can hook up B to the next one here. B. And then we have C naught. C naught here. D naught, we can hook this up here. Then we have BCD, so this should just be B, C, and D. BCD. Then we have ABC. Just going to organize this a little bit here. A, and then we have B, and we have C. And then we have another one, which is ACD, so I can just hook up to this one, A. Yeah, this goes to A, I think. C. Again, this is connected to C, so I'm going to hook up C here. And then we have D, which can connect down here. And there we have it. Those are our mapped inputs. And we take them to this OR gate here. So we know that just by looking at this truth table here, if A and C are on, or sorry, A, B are on, let's look at A, B is on, C and D are off, it should give us a 1, so that's true. Let's get us a 0, so if we do A, B, 1, D, 1, this should get us 0, yep. And if we look at, let's see here, just B being turned on, so let's turn off all of these. B, again, should get us a 1. We look at the truth table, 0, 0, 1. Okay, so if we do 0, 0, C, that should give us a 1 as well, and so on and so forth. So you can test this out in Digital Logic Sim. I'm going to have all these tools linked in the description. I think they're very useful for figuring this stuff out. And if you have any question, guys, like, please leave them in the comments. If you got any corrections, please tell me. It would be super helpful. But anyways, we've done this one. This one is a done circuit. Let's move on to the next one. This one is a little less complicated. This is just, I think it's, yeah, this is 4 variables. And it should be fairly straightforward. So I'm going to remove some of this. I'm going to delete this. Delete. And what we're going to be looking at is ORing, yeah, 3 variables. So do I have a 3 OR? I only have a 4 OR. So what I'll do is I'll probably take an OR gate here and OR it like such. So just hook up one of the ends like this. Anyways, we have 3 variables being ANDed, so we need 3 ANDs. Yeah, 3 ANDs. And what else? I think that's it. So we're going to, for the first AND, A negated, B negated, D negated, and then we're going to move on to the other term, which is A regular, C negated, D negated, so D go here, and then again A, and then just regular B, and D negated, so another D negated here. And this is going to get linked up to these OR gates, like so. And that should be the final circuit. Sorry about the mess here. So if, again, I check my K-map, or sorry, my truth table, we can look and see that, whoa, so A1 and everything else 0 should give us a 1. So if I do that, yeah, it gives us a 1. What would give us a 0? Well, we do 0, B1, C0, D0. So I'm going to do B1. B1 turns everything off like it should. So if I do CD1, like so, that also gets a 0 like it should according to the Karnaugh map, or sorry, truth table. Remember, we use the Karnaugh map to make the simplified expression. But yeah, so essentially what you can do is you could probably further simplify not the expression itself, but rather how the gates are implemented. So you could probably reduce the amount of gates that you're using. I know I have like 2 ORs. That could probably be reduced. That's basically it. So yeah, without further ado, I think I'm going to leave this video here, and thanks for watching, and I hope to see you sometime in the future. So bye for now.